I'm Chris with HVACR Videos, and we are here at Heatcraft Refrigeration Products in Stone Mountain, Georgia, and we are about to tour the R&D lab.
Chris, welcome. Good to have you here. Hope you enjoy the lab tour. Let me introduce you. This is Clifton Allen.
Clifton, nice to meet you. I have to say, I've never been in a research and development lab, so I'm really intrigued by everything that I'm hearing in the background. I could only assume that this equipment is running for a specific reason. I mean, are we monitoring things? Are we testing things?
Well, you know, that's a good question, because when I look at the lab, we kind of focus on two things.
Okay.
One is system performance, and that can come in a multitude of ways. Does it give me the performance I need? Does it meet the industry standards? But one of the more important things we're doing now, and probably more than we've ever done, is component qualification.
Okay.
Because we're having a tremendous problem with supply chain.
Right.
So, you know, our customers, when they order product, they want product. They don't want product that's missing a motor or product. So we are constantly going out to try to find new component suppliers. Okay. So if you look at the lab, you know, we go from everything from component qualification to component performance. You know, a great example is a fan motor. Okay, if you look at fan motors, they're pretty ubiquitous out in the field, but every piece of equipment we make has a special purpose motor. And what I mean by that is, you come over here, the motor on this evaporator has to be matched to the cabinet,
right,
and the coil.
Okay.
And the coil can have different thicknesses. So if I just take a general purpose motor, I'm not sure what I'm going to get. Okay, so what we do, and you'll see when we get to the code testers, we'll test that motor, and a lot of times we'll have to change the internals on it. We may have to add stack, because I'm getting too much static pressure, or we may have to do something with the windings. Okay. But at the end of the day, every evaporator has a motor that we call special purpose. Right. Okay, and that's a big piece of it. So then when you think about that motor, say I've got a supplier that I've been using for a long time, and he comes back and says, I can't get you the motors. So then we say, okay, we need to get another one qualified. In the old days, we'd go out and we'd get 200 motors, and we'd put them in the field, and we'd run them for 6 months. And then after 6 months, if they're still running, what do we know? They last 6 months. I don't know if that's going to be 6 months in a day. Yeah. So we needed a much more robust qualification process.
Now, how much influence do you have over the manufacturer, though? Do you know, in the past, okay, because I know supply chain shortages create havoc right now, but do you have influence over the manufacturer's R&D too? Like, let's say you have a manufacturer that you love working with. Do you guys go to them and spec and say, hey, I want you to make me this motor because you like working with that manufacturer and you've had a good track history?
It's definitely an iterative process.
Got it.
Okay, because as we look at it, as we say a motor, you know, we're getting too high a motor heat rise. So we'll go to them and say, you know, we're going to have to increase the stack. Well, what they'll come back to us and say, well, here are the stack options we have. So we'll work through those, and you know, it usually works pretty good. So they'll come to us, okay, if you need more stack, we'll give you a 1/4 inch more stack on it. It's going to lower the temperature as it runs. So every motor manufacturer kind of knows the process because they build the motors. Yeah. What I can't tell them is what incremental stacks they have. So we work through that.
So with that being said, I guess this is gonna probably make Heatcraft happy, but I mean, it really does benefit the contractor to stay OEM when we go with the motors instead of using aftermarket solutions because of the R&D that's gone into the motors that you guys have selected, right?
Absolutely.
And so that makes sense.
One fundamental challenge there, and that's performance standards. Yeah. Okay, if I put a general purpose motor in, I'll be the first to admit it's going to be easier to replace. Right. But it won't meet that target performance. So, you know, we're not against standards, we're in favor of good standards. So when we look at some of those, we know it's our responsibility to make sure when product ships, it meets it. And the way to meet it is to get a motor that matches the internal dimensions and static pressure on these. So it would be easier. It'd be easier for us. Yeah. But it's not gonna meet the standards.
And as a contractor too, I do have to admit that while, okay, let's be fair, OEM motors typically cost a little more money, but again, as a business owner, it makes sense for me to have my technicians using OEM because there's less thought process that goes into it. It's like, hey, just go get the right motor, part number, we're good to go, put it in there, and it's going to work fine.
Yeah, and you know, the other thing to remember too, you got the blades, and it's a combination.
Yes.
So, you know, when you look at efficiencies, the motor efficiencies with ECM motors are very high. I mean, the motor itself is about as high, but it's that combination of the air mover, the blade, and the motor. So it does make a difference.
As the R&D lab goes, how quickly do contractor gripes or issues make it back to you guys? So let's say, you know, in the field, we're running into a problem and we call tech support and we say, you know, these issues are really becoming a problem. I've changed 15 of these motors. Now, some of those complaints, you know, they may not be valid, but how many of those actually make it back to R&D? Does technical support relay that stuff back?
Yeah, that's a good question, because a lot of times you could put them in different buckets.
Yes.
Sometimes it's just a misunderstanding in the field. So working with one of our tech folks at AEs, so they can get that straightened out. Sometimes it could be that I had a shipment of motors that doesn't come up to spec. So what we'll do is we'll bring those motors in and we'll test them here. We always try, and that's another thing we do. We try to, if there's a field issue that's not something we can easily ascertain, we'll bring it in here and we'll try to replicate it. Okay, because like everything else, I talked to the motors one time. So we put those 50 motors out in the field, and if they work after 6 months, we needed more analytics.
Right.
Because as we're doing more and more of these, so now what we do is we get a motor in, the first thing we do is we look at that motor and we put on a code tester and it says, does it give us the CFM we need? Okay, if it does, I check off that box. Then I go through the UL safety. Does it meet all the UL safety requirements? If it does, check off that box. The third box is accelerated life testing. Okay, because the thing about it is if I look at a motor, I know that 80% of the time that motor is going to fail because it's going to be bearings or it's going to be windings.
Okay.
So when I have this new motor, I'll bring it in and I'll overload those 300 or 400%. And if I have a statistically significant sample, I can calculate mean time between failure with amazing accuracy. So now, instead of being able to say, I know this motor lasts 6 months, I can say this motor is going to last 8 years, and here's the data that shows it. The last thing, and kind of what you hit on, is I can get a good batch of motors, and they can pass all this, and then 6 months down the road, I get a bad batch. So the thing we do is, as we look at the motor, we identify what's on that motor that's critical to the quality, durability, reliability. And then we'll put measurement requirements in that we give to that motor manufacturer, and we go there to make sure they have process controls for those.
Yeah.
So it's a lot different than in the old days, but it's much more robust. And as you know, I'll give you another example: valves. Okay, if we can't get an expansion valve, and we'll look at the usual suspects, and I won't name them, but the domestic suppliers. Sometimes they'll have an allocation, we can't get them.
Right.
So we could go to Europe and get a valve. The problem is that valve in Europe's not going to have UL.
Gotcha.
Okay, so now what do? Well, the thing with this lab here is a client test data lab for UL. That means we can do the UL testing.
Oh, so now if you do the UL testing for that overseas valve manufacturer, does that UL testing then apply for them across the board? Or is it just for with your equipment?
Just for our equipment.
Okay, interesting.
Okay, and so if you come over here like that valve, I'll have to pressure test it.
Got it.
Because with UL 1995, now it's going to 6335-2-89. I know it's a number salad. Yeah. But what that requires me is I have to test that valve to 3 times working pressure. Okay, so I can do that here. I can even do it on higher pressure valves like CO2, where I can go to 6,000 PSI. But if I test it here and I do the 3 times, that's my UL test. I pass UL, I'm certified to use it on my equipment. Another supplier couldn't take that same valve and say, because Heatcraft tested it, I can use it for UL. So that's an advantage for us, but we didn't do it so much for that. We did it for expediency. You know, supply chain, we need to be able to qualify these components quickly. But we still have to follow the standard.
Yeah.
You know, I can't say, well, I didn't have any, so I put this valve in there. That's not going to work.
Now, how much of the R&D side, obviously research and development, But do the ideas solely come from R&D, or do you take input from outside sources too? Is there other people in the company that help with R&D? I'm going to bring up an example. I was recently installing one of these new evaporator coils with the intelligence setup, and I just ran across your new motor and motor bracket setup that makes it super easy to pull the motor with the blade still attached out of there without having to, disable and take the blade off, take the motor off, unbolt everything. And I thought that was a pretty cool thing, and it was one of the first times I've seen it. Now, ideas like that, do they come from the field? Do they come from a mixture of everything? Where do ideas like that
Mixture of everything, but that one there is the field.
Okay.
Because, when we get into some of the bigger racks, we develop new systems like CO2 transcritical booster systems with different technologies on it. So when we release them, my team, when we release it, we're the ones who designed it, we know it. So our field service guys that know our day-to-day equipment inside out, it's new to them. So we go out there and we do the commissioning and startup with them. And we'll do it over several jobs until they feel comfortable and take it over.
Right.
But that's some of the best things, because I'd love to say that we design everything perfect from the beginning. That would be a flat out lie.
Right.
Okay, we get out there and we realize as we're trying to work on it, it's one thing to put it together, it's another thing to take it apart.
Well, yeah, as a contractor, it's 10:30 at night. This is an emergency service call. This is the first time I've ever worked on this particular piece of equipment, and my head hurts trying to figure this out. And I just cut my finger because it's 0 degrees, and I just rubbed. So weird things happen. So you guys invite feedback from contractors from all sources to give you guys new ideas or ways to improve things.
We actually love having contractors come in. And we also, our field service guys, they'll be the ones giving us a lot of impact on designs. And then Mike can probably talk about that because he's more in the design teams. But the fact of the matter is, it's not a proudly found here. We love going outside and getting ideas, because the more people you involve in it, the more perspectives you get. Sometimes you can't see the forest from the trees.
Gotcha.
Now, in all fairness, Clifton's been doing this 22 years. I've been doing it a little bit more than that. There's a lot of smart people out there, and they come up with some pretty ingenious ways of doing things differently. One of the things we like is, because we're a global company, we also have product in Europe. And, even though we're doing the same thing, there's different approaches. So as you go to different markets globally, you see how people try to solve the same problem, but a little bit different.
Yeah.
And sometimes you say, that's not a bad way to do it.
And I think you're making this point, but I would argue too that you don't have to be an engineer. You don't have to have 1,000,000 degrees. You can just be a knuckle-busting mechanic that gets frustrated every time he works on something, and simply give that feedback back to tech support or email you guys or something like that. So, I imagine amazing ideas can come from anybody.
Oh, they absolutely can. And, one of the things I am really proud about our team is every one of them turns wrenches.
Right.
We have, when I look at our advanced team, we have a lot of advanced degrees, they all turn wrenches. You'll see them out in the field, they're going to turn wrench. They're inquisitive, okay? And they love talking to people, especially some of the newer ones, as they're trying to, because, no matter, there's no substitute for experience.
Right.
And someone that's out there every day can tell you, you don't even have to wait 2 seconds. You ask me, what could you do better? Bam, you're hearing stuff all the time. So yeah, absolutely. Those are the ones that can give you the insights that you'll never get just by looking at a unit in the lab.
Yep.
Okay, so when we were talking before about qualifying a motor, which is just a classic example, we've got this on a code tester.
Okay.
And this code tester, I can put different air volumes through it. So what I can do is, this has the coil that it's in the cabinet, and this is the motor I'm trying to qualify. So as I run the code tester, I'll do it at different static pressures.
Okay.
Okay, because if you think about it like an evaporator.
So this is like an environmental chamber then?
No, this is basically all CFM testing.
Oh, okay, gotcha.
Okay, we do testing, but this is just the air side.
Oh.
Because what I'm trying to do is I'm trying to match the motor blade combination to the static pressure created by the cabinet and the coil.
Gotcha.
That's what's unique, because every cabinet and every coil is different. I may have a coil that's got 6 rows, 8 rows. That has an impact on static pressure. So what I'll do is I'll run this motor knowing that I've got different coil assemblies, so I'll get this CFM at different static pressures, so then I can match the motor to each configuration.
And this may sound super simple, but again, as a contractor, as a technician working in the field, this just reiterates how important it is to stay with the correct pitch blade, to stay with the correct RPM motor. And yeah, you know what? We may change the pitch a couple degrees and it doesn't seem very important, but it really is, because we're talking about the airflow through the coil, which is going to adversely affect everything down the line.
Yes. And you know, it's not as big a deal on a condenser. It can be, but you know, if the condensers are cleaned properly,
yes,
it typically isn't. We'll assume that they do.
Right. Yeah.
I say that tongue in cheek.
I mean, of course, as a contractor, I want businesses and my customers to do more routine maintenance because that's more work for me. But at the same time, you know, they're cutting back on routine maintenance more and more every day, it seems, to try to cut costs. So, you know.
Well, it's pay me now or pay me later.
Exactly.
Okay, but the bigger issue is when you have an evaporator. Because if I don't know how that motor is going to work as the static pressure increases, ice on the coil,
yes,
that can cause some big problems.
Right.
Okay, so I need to qualify a motor not just for that steady state clean coil, but I also have to make sure I can qualify it when I get to higher static pressures. So that's all part of it. So once we get that nailed down and we've got a good match, then we'll go to our performance testing.
Interesting.
But that's a big piece of it.
Very interesting. So with, I mean, obviously with R&D, this is a no-brainer, but you guys are creating problems to try to replicate things we see in the field and to try to anticipate problems we're going to run into to see how your equipment performs, right?
Yeah, and you know, when we have a field problem, the amount of information we have associated can vary.
Right. Well, I imagine it's just a phone call saying your product is no good because of this, and that may be all you guys get, and then you guys have to try to put yourself in that technician's perspective and trying to recreate that problem with little to no information. I'd say majority of the time would be my guess.
Yeah, but if it's something like a blade that we have in a lot of use, we'll send a field service engineer out to meet the contractor, because the more we understand about what he's seeing,
yeah,
the better. Because you know, you can get into harmonics, okay? And 20 years ago, when we didn't have variable speed on everything, harmonics were pretty easy. And we can talk about that later when we get over there, but we test for low frequency and high frequency harmonics. But the interesting thing about it is to talk about low and high frequency, and now I take a compressor with an inverter, it's both. I can overspeed it, right? So I'm gonna get a harmonic there. I can underspeed it. And a lot of times that fundamental harmonic will come transient as I'm going from high speed to low speed and I go through this. So we spend a lot of time looking at high frequency harmonics, vibrations, frequencies, and low. And we always try to design it to where the fundamental frequency is way out. But it's a challenge now because everything's going to variable speed.
Yeah.
You know, in the old days, it's on or off. Now, I don't really like the old days because I like the new days because now I got a motor I can talk to.
Yeah.
Okay.
And maybe sometimes get feedback from too.
Absolutely.
Yeah.
That's the beauty of it. I mean, if you look at this stuff that you can do, if I've got a motor and I say, okay, I want constant CFM, well, as it starts to ice up, that motor is going to start to slow down. But now because I can talk to it, I can have it increase torque.
Gotcha.
So I can have it increase torque to keep that CFM until I get to a torque level and I say, you know what? It's time for defrost. Okay, in the old days, what I'd do is I'd put 4 defrosts per day, whether I needed them or not.
Right.
Say I'm in a fast food restaurant. Get young kids.
Yeah.
They'll go in, they'll open up a door, they'll leave the door open, they may shut the fans off.
Welcome to my world. This is my everyday working in restaurants.
Or you got a box that's got a gaping hole in the back of it, so you get all kind of humidity coming into it. So we got to understand that, you know, it's not all that simple.
Right.
Okay, so that's a big deal of it because, you know, we always say that you, like in grocery stores, you want 75-55, 75 dry bulb, 55% relative humidity. And if I put something in there and it's not working right, I can't say, well, your store's a little wet, because it may be a 20-year-old store. So the standard says I got to test for this, but we always test out of envelope.
Yeah.
So if it says I can go do 75-55, I'll do 80-65.
Right.
And if I can still get good performance at that point, I know I'm robust. So we test to the standard, but a tremendous amount of what we test is beyond the standard. Simply because if I look at a major chain that has 200 stores, 10 of them are probably brand new.
Yeah.
They're probably tight as can be.
Right.
And I don't have any issue. But that store that's 25 years old, they're not going to close it.
Nope.
And I can't say, well, you know, it didn't work because someone's opened the door on that too much. You know, so we have to understand there's a real world out there.
And I think that that's where things like your intelligence system with, you know, the capabilities of having alarms and different things come into play too, right? We can put all kinds of different features into there and try to notify the customer to prevent some of these problems from becoming catastrophic.
Absolutely.
Yeah.
You know, because the sooner you get to it, the better.
Right.
But the reality of it is, if you don't have someone going out there, you may have an issue that no one knows about until something catastrophic happens.
It happens.
You know?
Yeah.
So, you know, reliability comes in, you know, when we talk about quality, we talk about reliability, durability. There's a lot of aspects to it. But the bottom line is we're in food preservation.
Correct.
Okay. You know, we're a Lennox company, and I talked to my friends at the HVAC side, and I said, when your equipment goes down, someone sweats.
Yeah.
When our equipment goes down, someone can get sick.
Someone gets sick, or forbid, someone could die. I mean, you know, food safety is a big thing. So
yeah, no, it is. And, you know, there's a science to it.
yes.
So, I mean, whether you look at fresh cut produce and how the bags are done and temperature requirements, there's a lot to it.
Yeah,
So there's more than meets the eye, there's no doubt about
for
it.
sure.
But our job is to make sure we're as robust as possible. You know, we also have to be conscious of costs, but I think there's a happy medium where we can do both. Okay, so what we talked about so far was component qualification. We got to do system performance testing too.
Right.
So this is a set of our DOE rooms, and we'll be talking a little more about AWEF
Okay.
and qualification, but I want to show you these rooms. And what we have is we have 3 sets of them. This is the medium size.
Okay.
So all of our evaporators, we have to match capacity to volume of the room.
Right.
So I need multiple sets. So what you see here is a unit cooler, low side, and on the other side, it's the high side.
Okay.
Again, everything is off of LabVIEW, because when we do these tests, we have to make sure we document it and we have a chain of control on that data. So if the DOE comes to me in 5 years and says, I want to see this test data and it's AWEF test on this unit you did 4 years ago, I need to be able to show it to them.
Gotcha.
Okay, so that's what we use the LabVIEW for. But when you look at the rooms, this is the low side evaporator room. If you look up, you'll see an evaporator.
Okay. Yeah.
Okay, so the interesting thing here is the way the code's written, I can test units as a match pair. So I can have an evaporator and a condensing unit, and I can run that test.
Okay.
But that's really not reasonable for the standpoint that there's no way to know what this evaporator is going to be hooked up to or that condensing unit. So the number of potential match pairs are infinite. There are times we want to do that. Say I'm using my condensing unit with a customer's ice machine.
Uh-huh.
Okay, so then I want to do a match pair. So, but we can also test them individually. So I can test this evaporator for AWEF by itself, and I can test that condensing unit. Okay, so I can do them individually, or I can do them as match pairs. That was one of the discussions we had with the DOE, because originally they just wanted to do match pairs. When we explained to them the infinite number of combinations, it was an agreement. So we work with them. They're reasonable. We always try to make sure we get a good outcome from what the regulation is. But what you also see is, if you look on the wall there, you see 2 flow meters. Everything's redundant. So all of the instrumentation on these rooms is redundant. So
Okay.
these rooms, they're custom rooms, they're extremely expensive, but we have to get to the test method. I can run the test and get an AWEF, but if I don't have the instrumentation according to the test method, it's not a valid AWEF. Now, I get the dual instrumentation, I end up with the exact same result, but now I can certify it. So that's where a lot of cost comes into these rooms. But again, This one is my evaporator side. This is my condensing unit side.
Okay.
I can run them individually. I can run them as matched pairs. What you'll see over on the other side of the lab is we have another pair of these for smaller, and we have a much larger one for big. Because again, I can't just test a small evaporator in one of these rooms, because there has to be a ratio between the capacity and airflow of the evaporator and the volume of air in the room. So again, that's why we have so many DOE rooms.
So in the R&D lab, of course, you guys are trying to look at the future, I would imagine. You guys are trying to anticipate regulation changes. You're trying to lead the way and innovate. But I guess you guys probably get to have fun in here too, right? I mean, you obviously, I'm looking up and I'm looking at all this ductwork on these walk-ins. So I would imagine that these are there to, you know, when you're dealing with A2Ls and different types of refrigerants, to protect you guys. But you guys get to do some fun stuff. You guys, I would imagine, get to blow things up. You get to, you know, do different. I mean, it's got to be a little bit of fun in it, right?
Yes, especially when we get to the advanced technologies. We'll talk about transcritical booster systems.
Yeah.
Our objective is to blow things up.
Gotcha.
Okay? I mean, it really is. Because if we blow it up, then we know how to make it more robust.
Right. You know,
so
the limitations.
that is the fun part of the job. Because what I tell everybody is, you can blow something up once, but if you blow something else up, it may don't make the same mistake twice.
Right.
Okay? But if we're not making mistakes, we're not pushing the envelope.
Right. Your job is to push the envelope, find the failure points, and decide if you want to push past that or what you want to do to change it so you don't have those potential failure points.
And we're also looking at non-traditional cycles. It's not just vapor compression. So that's kind of fun too, looking at it. We spend a lot of time with universities. Okay, so you were talking about, do you go outside? We always go outside. Okay, because it's a force multiplier when you're working with different entities, whether it's contractors, whether it's universities, whether it's national labs. Okay, so that is the fun part, but we still have our day job.
Right.
Okay, and we got to make sure that the products we sell today meet the standards today, but we also know what that standard is going to be possibly next.
Gotcha.
So, you know, yeah, we're testing to the AWEF as it is today, but in the other engineering groups, they're working on that next gen because they know that those regulations are just going to get tighter and tighter and tighter.
Now, I would imagine it would benefit you guys to work with government agencies so that way you're aware of the potential changes that are coming ahead, correct?
It's absolutely critical.
Gotcha.
Okay, whether it's the federal, DOE, EPA, California CARB, CEC, because what's kind of interesting, and I know it'll be talked about later in some of your conversations, is they don't necessarily have the same agendas.
Right.
Okay, the EPA, they're about environmental, reducing refrigerants, going to friendly refrigerants. The DOE is all about energy efficiency. And I think they're starting to talk a little bit more, but that's something we have to manage. But we love the fact that we get in early and we can have discussions. We have a seat at the table. And our industry does. But that's a really, really important thing because we don't want all of a sudden someone hands us a letter and said, this is what you got to do. We want to know what's being discussed, what's possible, and then pros and cons. Because we're not against regulation, we're against bad regulation.
Right. And
what I mean by bad is if I have to do an energy efficiency improvement, but the payback to the customer is 10 years, I'm going to say, is this really the best? You know, and we'll always do max technology.
with that being said, the government agencies, I would imagine, take feedback from you too, right? I mean, do you get to say, hey, you know, yeah, we can meet this, but these are going to be the ramifications of these? Do you give that feedback to them too?
Absolutely. And you know, the thing about it is they work with consultants that will work with us.
Got you.
And I know there's going to be a lot more discussion on that later, but that's a very robust part of the process. Because they need that. You know, the DOE will get rulemaking authority from Congress, but the DOE is not experts in refrigeration. So they'll get consulting firms that are experts. This is a DOE room too.
Okay.
But the thing with the DOE rooms is I have to match the size and the capacity of the evaporator to the volume of the room. So as my units get bigger, the room gets bigger.
Got it.
So as you look, some of these units, and this is only a 1-fan version, I go up to 3 fans. So as you can see, I've got a lift in here but you'll see dual instrumentation
Yeah.
like you see in all the other rooms. So these rooms are built specifically to the test method.
Got it.
Okay, and if you saw the horsepower on the back end of this room, we've got 160 horsepower screws just to do the room control, because I can take this room down to -20, I can take it up to 120.
Now, when you said about the DOE testing, how hot do you certify your equipment, actually, besides DOE, just in general, to operate in? Like, what conditions? I mean,
I'll rate them.
You'll rate them?
Yeah, I'll rate them, but I don't certify them to them because there's no standard to certify them at the higher temperature.
Got it. So you rate them at 120 degrees?
Yeah.
Yeah.
Because, obviously, the higher the condensing temperature, the lower the capacity.
Right.
So, yeah, so when you look at our tables, we'll have it rated for those.
Yeah.
But the AWEF certification doesn't go, it's the 95.
Got you.
But it gets to what we said before. I rate to a standard, but the real world doesn't follow the standard.
Yeah. Yeah.
This room here is where we do A3, flammable testing.
Okay, so
it could
like
be
propane and isobutane.
Yeah, primarily.
Okay.
And obviously there's charge limits.
Yeah.
So you 150 grams, but it's going to be going up, maybe eventually getting to 500. But that's why it's typically smaller equipment. Like up here on top, you see that Pro Cube unit. That's a package unit.
Right.
So it will have a charge well below 150. But I need to test them. I still need to get to that AWEF. It's a different test method, so I don't use the rooms we were using, but this room is set up to do the AWEF testing for A3s.
So as a layman, just as a contractor, I work with a lot of R290 systems, and things that I notice is the equipment, the condensing units, the line sizes, everything is much smaller. I'm actually amazed with the refrigerant charge, what you can do with 150 grams or less, and how well it can actually cool. I know there's a lot of fear in the industry about flammable refrigerants, but something that I've always told people is it's really, yes, there's some safety things, but if you go back to the things that we forgot about basic refrigeration, the proper practices with A2Ls really isn't much different. The only thing we're gonna say that's really gonna change is, yes, you do have the very slim chance of a fire or something, but the proper practices of cutting components out before you work on them, of purging the system with nitrogen while you're brazing, those have been basic principles that we're supposed to follow from the beginning, but we kind of have forgotten them. So there's a lot of fear right now when it comes to A2Ls, and not that I'm laughing at people that are afraid of A2Ls, but when it comes to hydrocarbons, on the refrigeration side, for the guys that do just air conditioning, they don't realize that hydrocarbons have been huge in other countries for a long time, and they've come to the US now. We're working with them on a regular, and I don't think it's that big of a deal. I don't mean to discount people's problems, but it's very interesting in how efficient the hydrocarbon refrigerants are.
Yeah, they are. If I look at propane, for instance, it's so similar to 22.
Yeah.
Which was a good refrigerant. It's a good refrigerant. Now you have to, look at isolation, ignition sources, stuff like that. But at the end of the day, you talk about purging with nitrogen. I hope everybody purges with nitrogen, regardless of what they're putting in there. But as far as propane, I kind of laugh from the standpoint that, you're starting to see home refrigerators with it. But everybody say, oh, it's propane. Well, you got a gas stove sitting right next to that refrigerator, and now you look out your back window, and there's a 10-pound tank of propane that you're barbecuing with.
You have a 60 to 100,000 BTU furnace in your house running off of natural gas. You're driving a car sitting on a tank full of gasoline. Now, again, there is valid fears. We don't want to discount everything. There is proper practices we need to follow, but it is also, I guess, maybe ironic or something, some of the fears, that people have.
Yeah, and again, it's natural.
Yeah.
And propane, it's heavier than air.
Yes.
So if it does leak, it's going to go down. So making sure you have proper ventilation at the bottom of the unit, you don't let it pool anywhere. People are going to get more used to it, and I think you're going to see more acceptance of it. But there's going to be that upper threshold.
As a contractor, one of the biggest fears I have when it comes to working on hydrocarbons is actually a silly one, and it's when it comes to removing the refrigerant charge. That one, because we're so ingrained to recover the refrigerant and properly dispose of it when normal practices in a safe environment, you're allowed to vent that refrigerant. So that one is just one of my biggest things because it doesn't seem natural for me. When I'm working on something that it's like, okay, we're going to go ahead and vent this charge into the atmosphere. And it's like, wait, I'm doing something wrong. Like, I'm not allowed to do this, you know? So that's one of the weirdest things for me is having to do that.
Yeah, you know, and again, the charges are so small.
Yes.
I don't think the average person realizes how many times they're around a unit that's being powered with propane as a refrigerant.
I would be safe to say that if you have a refrigerator in your home that's been manufactured within the last 5 years, it's pretty much certainty that it has isobutane in it. That's pretty much, you know, a standard.
Because it's a perfect match.
Yep.
You know, so there's no silver bullet, okay? Especially when you look at regulations. You know, you're going to have smaller systems with hydrocarbons.
Yep.
Okay, it's a great fit. But as you get over that, you're going to get into A2Ls coming into the market. But then you get over a certain limit, then you're going to have to go to something below 150 GWP. And then you're going to be looking at CO2. So, and we work with the chemical companies all the time. In fact, we get new blends in all the time of the A2Ls. I can't say which one's going to win yet. There's going to be several of them. But the bottom line is, I don't think we're going to get to a place where, for all applications, there's going to be one refrigerant. You know, you get into the upper, you're looking at ammonia. But ammonia's got a lot of overhead. So then you come down into the HFC world, which will now be the A2L world and the CO2 world. So, you know, our job is just to make sure that people have choices and that we're making the right choice of refrigerant to the application.
Opinion question. Do you think, and as an R&D person, do you think that eventually, because in my head, the way that I think of regulations in the industry and everything that's going to happen is if you can think it, it's going to happen. That's the way that I think. If you can think of a new regulation or something, it's eventually going to come. Mm-hmm. Do you think that CO2 will become mainstream when it comes to light commercial refrigeration and home refrigeration?
This is an opinion question?
Yeah.
Yes. The problem, CO2 is a good refrigerant. There's technologies I can show you that work that's going to make them even more efficient that haven't hit the market. The problem you get in is that cost curve. And CO2 systems, by their very design, have variable speed control.
Right.
So you got that on the compressors. A lot of times, so when you get into smaller condensing units, you're looking at a 3 to 5 times multiplier today for that cost of that CO2 system. Guys buying that condenser unit, all he wants to do is keep his damn cooler cold.
Yeah.
He doesn't want to wear a badge saying, look, I spent 5 times more for that condensing unit, but I'm green. Okay, I mean, if they didn't need refrigeration, they wouldn't put it in.
Right.
Okay.
That's a good point.
So it's going to come down, but I think you're going to see a natural threshold. But I also think that you're starting to hear stuff in Europe that it's going to be a problem. So that's my opinion.
Interesting. So, okay. So I think I have an idea what's going on here, but kind of explain it to me. What are we doing by shaking this evaporator?
2 things we're doing. One is we're trying to mimic what it's like in transport.
Okay.
So this is before I was talking about low frequency and high frequency. When I'm transporting a unit, it's low frequency. Okay, so I can mimic with this. So I can mimic a truck with air springs or just springs. So I can mimic that. But I package units and I ship them. So I'll also do it for testing packaging to make sure I'm okay. There's standards that tell us, like, this is not actually attached. It's free. It's sitting there free.
Okay, got you.
So this is the amplitude for the standard. But then we'll go in and we'll dial it up. Okay, and it gets pretty crazy when you dial it up because that was that added envelope.
Yeah.
I don't want to just meet the standard, but so, you know, transportation is a big piece of it. And we do get a lot of damage that can happen because a lot of times you don't know where that truck went. And to tell you some stories on that, but that's for another time.
Yeah.
The other thing we have to do is high frequency.
Okay.
That could be blade pass on a unit. That could be gas pulsations from a compressor. So we do a lot of finite element analysis where we'll take racks that run and we'll put accelerometers on pipe to just see, you know, what kind of vibration are we getting. And then we'll do finite element analysis to see, does that put us near a fundamental frequency? So both low frequency and high frequency is a big deal. And like I said earlier, because we have so much variable speed out there today, it used to be whatever it ran at one frequency.
Right.
Now it runs through a range of frequencies. So that's what this is for.
Interesting. All right.
Okay, we talked before about new technologies. Well, this is a transcritical booster rack, but this is our test bed.
So transcritical booster, forgive my ignorance, but this is CO2, right?
Yes.
Okay.
Okay, and the CO2 has some unique characteristics. One, it goes supercritical.
Okay.
Okay, so when you talk about CO2 systems and they're supercritical, the condenser becomes a gas cooler.
Gotcha.
Because over 88 degrees, CO2 can't condense.
Okay.
And as you know, in California, you're going to have days you're going to be way over 88 degrees.
For sure.
So what ends up happening is the gas cooler, not a condenser, cools the gas, and then it comes into the system. But the booster system is pretty simple. I've got medium temp compressors and I got low temp compressors.
Okay.
So what'll happen is I've got, say it's a store, say it's a cold storage facility, I got medium and low temp loads.
Right.
I run them both. So the medium temp or the low temp compressors will take the return from the low temp loads and they'll boost them up to the medium temp pressure. So the medium temp compressors will take the low temp discharge and also the medium temp return.
This is kind of sounding like a cascade system.
Very similar, but in a cascade system, they're individual loops.
Got you. Okay.
Okay. In a booster system, they're all in the same loop.
Got it.
Okay. You'll see different pressures. But that's basically it. The low temp gets boosted by the medium temp
Interesting.
up to the gas cooler. Okay. So other than that, I'd say 85%, the skill sets are they're the same as HFCs.
Got it.
There's some interesting things. You got higher pressure. So if I look at an HFC system, it's probably got a working pressure of 450 PSI. On a transcritical booster, it can go up to 1800.
Okay.
Okay, but the characteristics of the system are the same. The one thing you always talk about charging is a lot different on these.
Got
Okay,
it.
so when I charge a transcritical system, I have to start off with vapor.
Interesting.
So as I charge it, I want to get the pressure in the system up to about 150, 200 PSI. Because what I don't want to do is get dry ice.
Oh, okay, okay.
Okay, and dry ice can cause a lot of problems. So I charge it with vapor, I get it up to that point, and then I finish charging with liquid.
Interesting. Okay.
Okay, other than that, it's pretty much the same. It's higher pressure, but you know, as we do startups on these racks in the field, we'll get contractors that this may be their first transcritical rack. And what I see almost every time after we do it, they always say, well, that's not that different. Because it's not. You do have to watch out on where it is different. Okay?
Yeah.
Higher pressures. For instance, when you get into the higher pressures, I can't use normal copper.
Right. That was a point I was going to make was, again, I've never worked on CO2, but I pay attention to social media and I have friends that do, and I've seen horror stories of technicians making quick decisions because they ran out of a certain pipe, and then they'll go use the wrong type of pipe, and then you have critical ruptures, you know. And it's interesting too, when you see it, you could tell there was a lot of pressure behind that rupture because it splits the pipe in a long length and it's pretty catastrophic.
Yeah, and again, that's a good point, because when you get into bigger diameters, because the bigger the diameter of the pipe, the thicker the wall needs to be.
Yes.
And you get to a point with copper that the copper, you no longer do it. So now you go to a copper iron alloy that gives you more strength. But then that can only go to a certain diameter. And then once you get like over that, then you got to go to steel.
Interesting.
Okay, but you know, the skill sets are brazing the copper iron is really no different than brazing copper.
Now, when you're brazing, so do they not use just regular copper at all? Is it always copper iron?
No, they're in the low side of the system, like on the low side, it's 350, 400 PSI, so that's regular copper.
Now, what kind of solders are they using? Are they
Same
using
solder.
like 15%, or are we going like the high silver content solders, like 56, 45?
It's no different. When we go to the higher silver content, it's probably because it's a much more complex joint,
Gotcha.
or it's just similar metals.
Yeah,
It's no different.
for sure.
Okay, so again, the higher the silver content, the more robust the joint's going to be.
But just the higher the cost. But
Right.
on a system like this, I imagine the costs matter, but the customer probably understands the costs are going to be high, and that's part of their budget plan.
Yeah. Well, but the other thing too, you got trade-offs. Okay, so
Yes.
when you talk about the cost, copper. When I look at CO2, the diameter of the pipe gets much smaller than a traditional HFC.
Oh,
So I'll save on material
right.
in some areas, but I have to give it back in other areas. So there's trade-offs. But a lot of times what you'll see on evaporators, if it's an HFC evaporator, it'll have a 1/2-inch tubes. If it's a CO2 evaporator, it'll be 3/8 or 5/16.
Now with CO2, are you getting oil movement throughout the system just like a normal refrigeration
Absolutely.
system? Okay.
And you know, I have coalescing oil filters.
Right.
This one here, I've got both coalescing and I get helical because I'll test different technologies.
Okay.
But yeah, absolutely. And we have our own patented oil separators too.
Oh, okay.
Especially on the small rack there. So the bottom line is there are differences. They're not significant as long as you're trained in. Because, for instance, these systems see 3 pressures. The high side pressure, which is the gas cooler area, that can get up to, we rate it for 1800 PSI. The intermediate by the flash tank, that's around 550 PSI. And then when you get in the low temp, it's like 350.
Okay.
Okay, so it's a little different, but at the end of the day, it's more alike than it's different.
It's still a refrigeration system. You're still transferring heat.